Hello students, good evening. Welcome to Wallah. My name is Venkatrao. Welcome to the lecture series of Theory of Computation. So today is our lecture number 13. In our previous session, we have studied push-down automata. Push-down automata, one of the very important concepts of our second topic, context-free language and push-down automata. When in our automata concepts, this is the second automata we are studying. So first finite automata, important one. After finite automata, most of the questions will get in the gate examination from this push down automata concept, right? So before going to start, let me recap what we studied in the previous classes. This is the push down automata, its diagram, block diagram, as well as formal definition. So push down automata is nothing but finite automata. This total structure is comes under finite automata plus one stack. Finite automata, one stack. This together is called as push down automata. So here this finite automata structure, finite automata plus stack. This together is called as push down automata. So how to construct that we practiced in last two classes. So PDA construction, for that we have taken two classes. The first class we understood what is push down automata, definition of push down automata, formal definition of PDA, and how acceptance methods. There are two acceptance methods, acceptance by empty stack, acceptance by final state. So in the first class roughly we try to understand the PDA. In our yesterday's class we constructed push down automata, complete construction we did in the last class. So we constructed PDA for so many languages. In today's session also we try to, today's session is all about context free languages, CFLs. We try to understand what is context free language, for what type of language PDA possible, what are not context free languages, for what type of language push down automata not possible, for which possible, or all those things we are going to study in today's session. So when not possible is the language for which PDA not possible are not context free languages. So first we will see not context free means PDA failure, PDA limitation. So there are some languages for which PDA is not possible. So first let us see what are the languages in which case PDA fails to recognize. Let us try to see, and then what is the reasons for what type of languages DPDA is possible, NPDA is possible. That DPDA, NPDA clarification also we are going to study in today's session. So this is what the today's topics, right? In today also let us try to construct push down automata for one of the important language, that is first let me construct for 𝐶𝐻 power r, W belongs to A plus B whole star. Let us try to construct the PDA for this. Now the PDA construction is very simple for us. What is this 𝐶𝐻 power r? Before C whatever the W is there, after C same W. So for that, before until C comes, we will push everything into the stack. See the, look at this. This is a palindrome. 𝐶𝐻 power r is nothing but palindrome. I told you previously, palindrome things we studied in regular concept. Palindromes we studied in regular expressions time. For palindromes we concluded in regular language time. Now palindromes PDA. This is an odd length palindrome. So a string and its reverse whenever is there, that is a palindrome. So generally let us see what type of strings exist in this. Assume we have AB, before C, after that BA. I told you to construct PDA, what is the minimum requirement here? To construct push down automata, the minimum required thing is logic. First identify logic. If you identify logic, then we'll try to construct the PDA for that. See, whenever the string is reversed, this is our W, this is W power R, W power R. So, if you want to construct PDA, see what is happening. Once the string is till this part, okay, after C, this is reverse, no? So, last symbol becomes first symbol. These two same, this and this same, this and this same. This is what happens. Whenever a string is reversed, the end of this string, end of the W is nothing but first symbol after C. Because string is reversed, this is what we have to verify here, whether this type of strings present or not. So, the logic is nothing but until C encounters every possibility of W, we have to push into the stack. Initially A comes, push, B comes, push, same symbol, push, different symbol, push, everything we have to push into the stack. Whenever C comes, then we skip that. We don't perform any push, any pop. After that, see what happens. After that, if it is a valid string, the first symbol, top of the stack symbol should be same. First symbol, top of the stack symbol, same, pop. So the logic is push W. Then pop for same symbol. This is the logic. Push W and pop for same symbol. So this logic we need to maintain. In order to implement this logic, we have to construct the push down automata here. Right. So let me start construction of this automata. Start from the state Q0. In Q0, every possibility push into the stack. Initially A comes push. So in Q0, initially A comes push, B comes push, whatever it may be. After that, same symbols, push, different symbols, push, every possibility is push. That's why my transitions will be 𝐂𝐳0 or 𝐵𝐳0. Initially, whatever it may be, push into the stack. Then same symbols, reading top of the stack same, reading top of the stack same, then push into the stack. Reading top of the stack different, reading top of the stack different, then also push into the stack. In every possibility we have to push into the stack. Initially A encounters or B encounters, reading top of the stack same, different, every possibility push into the stack. Whenever C, top of the stack is C. Right. Whenever C is there, then we need to observe top of the stack can be Z0 or top of the stack can be A, top of the stack can be B. Whenever C, we don't push, we don't pop. Whenever C is there, no push operation, no pop operation. Only whatever is there in the top of the stack, maintain as it is. Then that becomes a skip. Just read the C and skip. Don't perform any operation. That's why we don't represent any push representation. So, or pop representation. Maintain whatever is there in the top of the stack as it is. If you maintain, this is called as skip. We just read the symbol and will perform skip. Then after C, here the main logic. After C, coming symbol top of the stack same. Coming symbol top of the stack same. Then we need to perform pop. So here coming symbol top of the stack same, perform pop. Coming symbol top of the stack same, perform pop. Reading symbol top of the stack same, pop. Reading symbol top of the stack same. Finally, if it is a epsilon in this, epsilon z0, go to the final state. This is the push down automata for palindrome, odd length palindrome. I will explain this once again. So transitions looks somewhat lengthier, but the automata structure is very easy. So the logic is very simple. Initially, whatever is there, initially either A or B, initially whatever the situation, we have to push into the stack. Initially either A may be there or B may be there, push into the stack. After that, whenever reading symbol top of the stack symbol, both are same, different, every situation push into the stack. So these two transition goes to initial, then these two goes to same, this will goes to different. Whatever it may be, initially we have to perform push until C. Until C, every possibility is push, but whenever C, on C, we'll skip. We'll just read it, we'll skip. That's why whatever is there in the top of the stack, maintain as it is. After that, reading top of the stack, same, perform pop. So A on A, perform pop, B on B, perform pop. Reading symbol top of the stack, that is the logic here. Whenever reading symbol top of the stack same, our WC W power R concept is achieved. WC W power R, WC W power R, like this. This case, so in this case, whenever epsilon encounters, input is ended. Same symbol we are performing pop. Input is ended. Stack symbols also ended. Z not presents. Then our string is a valid string. We have to go for acceptance by entering into the final state. So this is the push down automata for odd length palindrome. So very easy one. So logic is the main thing. So if you construct a logic properly, based on this logic, implement the logic just by using transition diagram or transitions notation. Any notation is okay, whether it can be transition diagram or transition notation, then the PDA will be ready. Right. Let us try to construct PDA for similar kind of thing, even length palindrome. So this is the odd length one. See the length here. So 9, odd length palindrome. Generate anything, it's an odd length palindrome. Now let us try to construct for even length palindrome. So the even length palindrome generally would be written as W power R. W belongs to A plus B whole star. Now we need to construct the push down automata for this. W power R, W belongs to A plus B whole star. There is a difference between previous language and this language. What is the previous language? WC W power R is there. That means there is a separator. Before in the middle of W and W power R, there is a separator C. So until C comes, until C whatever is there, we will push into the stack. After C, whatever is there, for the same symbol we will perform pop. So until C, everything is push. After C, same symbol pop, this way. But here, separator C is not there. Separator C is not there. Now the question comes, till what part we have to perform push. Now it is a machine. Assume we have a string of kind like this. The machine is reading. Machine reads from left to right. Then after some time it has to start performing pop. How it knows? This is a 6 length one. Assume I have given 1 lakh length. So how the machine knows where is the half of that part? Previously separator C is there. So till C it is continuously performing push. After C started pop. Now here the question is when the machine has to start pop. That is a major concept here. So that's why. So the question is, can we construct push down automata for this? Can we construct push down automata for this? Most of the students will say push down automata not possible, NPDA possible. That is wrong answer. So PDA possible here, push down automata means NPDA only. But here the confusion is there on operations. When to perform a push operation, when to perform a pop operation. Whenever you have these type of confusions, then deterministic push down automata not possible. We have to construct a non-deterministic push down automata for this. So for this language, the answer is DPDA not possible. But NPDA possible. DPDA not possible, but NPDA possible. What is the difference? So lot of difference here. Expressive power of NPDA is more than DPDA. That is what we studied in previous classes. Means what? NPDA will accept so many languages even though those are not accepted by DPDA. This is the best example. So the language, whatever we have written here, WW power R, WW power R. So this language is clearly accepted by NPDA but not accepted by DPDA. When this situation arises is, if you don't have a confusion in, if you don't have a clarity on operations, if you have a clarity on operations, when to perform push operation, when to perform pop operation, clearly deterministic PDA we can construct. But there are some languages for which clarity will not be there. So when to perform push, when to perform pop, sometimes confusion arises. Whenever this confusion is comes under non-determinism. So for these type of languages, we have to construct non-deterministic automata, right? So let me explain this, where is the problem, and through some example, then we make a logic, we try to construct the non-deterministic PDA for this. So for this WW power R, we can construct PDA, that is a non-deterministic PDA. So PDA, non-deterministic PDA, both are same. DPDA is not non-deterministic PDA, expressive powers are different. So for this, PDA possible but not a DPDA. This is the way you have to answer, right? Now let us take some example string. Let us try to construct. Assume I have A, B, B, W, B, B, A, W power R. We have a stack, we have a input. Now let us try to observe the logic here. What is the logic? Same as previous one. Initially A comes or B comes. Initially A or B push into the stack. First we have to perform push operation, push into the stack. After that, see, reading symbol is, the next symbol is B, top of the stack is A. So whenever reading symbol, top of the stack are different, reading symbol, top of the stack symbol are different. Whenever reading symbol, top of the stack symbol are different, Definitely we have to perform push operation, because once the string is in W power R, see, if the machine is reading W power R, the W power R only possible operation is nothing but pop operation. Whenever we enter into W power R, reading top of the stack becomes same. Look at this. This is the W power R, no? It is same. It is same. It is same. Different is coming means what? Reading top of the stack, different is coming means the string belongs to W. This is the indication. This is the logic. Like this, we have to make a logic. So whenever reading symbol top of the stack symbol are different, the meaning is clearly W. Reading symbol top of the stack same means it can be W, it can be W power R. Their confusion starts to the machine. That's why till this part, okay, both are different. We have to perform push operation. Now look at this. Reading symbol top of the stack symbol are same. Whenever reading symbol top of the stack symbol are same, no confusion starts to the machine. What is that confusion? Whether the same situation belongs to either W or the same situation belongs to W power R. This is the major confusion here. So there is, we cannot determine the string can belongs to this part, the string can belongs to this part, because reading top of the stack same possibility is there in W power R, whether it is W string or W power R string, because if it is W string, machine has to perform push. W power R, machine has to perform pop, but it cannot determine whether it is W or W power R. Here the non-determinism takes place, right? So this is the major thing here. So this is a small string, that's why you can say same here we'll push, here we have to push, but here for the same situation we have to perform pop. How to know that? If it is a big string, 100 length or 500 length string, how it knows whenever same situation comes? So here there is a possibility of confusion. So in these type of languages, we have to construct for non-deterministic PDA. Whenever like this, multiple possibilities, input, reading input, top of the stack, on that situation, multiple possibilities, push possibility, pop possibility, if both are exist. In these type of cases, clearly deterministic fails. We have to go for non-deterministic concept, right? That's why this language is accepted by NPDA only, but not by DPDA. Here there are so many languages of this kind. Because of this reason, the expressive power of NPDA is more than DPDA, right? Every NPDA cannot be, whenever expressive powers are different, every NPDA cannot be converted into DPDA. But in finite automata, every non-deterministic finite automata can be converted into deterministic finite automata, because their expressive powers are same. But here expressive powers are not same, that's why it is not possible but for DPDA, right? Now we understood this is the language where DPDA not possible, NPDA possible. Now the question is how to construct. So we'll start constructing this. For this I will show both notations, transitions and transition diagram, then it becomes easy for you, right? So initially let me construct a new one. It requires so many transitions. So I think I will divide this board into two parts, because in one part it is not possible. First, what is the initial situation? Initially either A comes or B comes, push into the stack. Initially A may comes or initially B may comes. Initial situation is simply push. So initially either A is coming or initially B is coming, we have to perform push operation, push into the stack. Then Reading symbol top of the stack are different. Reading symbol top of the stack are different. Then also no confusion to the machine. Whenever reading symbol top of the stack are different, what is the possibility machine thinks? Reading symbol top of the stack are different, then there is a push possibility because the string belongs to W. If this is the situation, then also we will perform push operation. Reading symbol top of the stack are different, push. Now whenever reading symbol top of the stack same, then confusion starts. Assume it is belongs to W. If you don't know exactly, to show. If it is W power R, we have to perform pop. Don't know which is, it is a push or pop. So what we will do is, we have to show both the notations, this or this. Either it can be this or this. Like this, for one transition, multiple possibilities. This multiple nature is comes under non-deterministic one, like this. And then once you enter into QR, whenever it is Q1, that is W power R. It is a W power R, simply pop. If it is a W power R, we have to perform pop. Finally, acceptance. Acceptance by empty stack. Q1 epsilon. That's all. So for this, I'm making a small change. Take this as a positive closure. So that only string starts from A onwards, one symbol. Right. So same thing, let me show in transition diagram. Initially, let me write the states. All initial situation. What is the initial situation here? Initially A comes or B comes. Push. A comes push, B comes push. A encounters push, B encounters push. Reading and top of the stack are different. No confusion. Reading and top of the stack different. Then no issue. Then it is very clearly we have to perform push. Whenever same, whenever same. Now the problem encounters. If it is W belongs to W, we have to perform push. Belongs to W power R, we have to perform pop. What is this one? If you observe here, both possibilities are there, so we have to show both possibilities. This is my W state, this is my W power R state. See, for this same situation, from the same state, sometimes performing push, sometimes performing pop. We cannot determine exactly what we have to do. That if you are unable to determine exactly, that comes under non-determinism. So this is a non-deterministic machine, because clearly on the same situation, multiple operations, sometimes push operation, sometimes pop operation. Then for same reading top of the stack same pop, reading top of the stack same pop. Finally, on for previous one I am showing by empty stack. Now I'll show by using final state in the diagram method. Epsilon Z0, make Z0, enter into final state. Where the non-determinism exists, the non-determinism exactly exists in his. So this is the place where non-deterministic concept is present. We can construct push down automata, no doubt. For WW power R, we can construct push down automata, but that push down automata is non-deterministic one. It is not deterministic one. So this language is non-deterministic context free. It is not deterministic context free language. Like this we have to pronounce. So for this we cannot construct a deterministic automata. That's why expressive power is completely different. This is one of the very important language asked in GATE paper so many times. This question asked in GATE paper for so many times. Right? So whenever we are studying push down automata, these palindrome languages, this is a even length palindrome. Palindrome languages are very, very important. So for palindrome languages, can we construct push down automata? Means definitely we can construct. We can construct push down automata. There is no problem. But we cannot construct a deterministic one. That is the only thing. That's why if you see the relation between this, the PDA so NPDA DPDA NPDA and DPDA. So based on their different expressive power, so this is a more powerful one. This is a more powerful one, NPDA than DPDA. Based on this nature, language is also classified. The languages are nothing but NCFLs, non-deterministic context-free languages, also called as CFLs. These are called as deterministic context-free languages, DCFLs. Like this, language classification also done. And if you see the relation between these as well, DCFL comes under here, CFL, that is non-deterministic CFL, comes under here. If we categorize the languages, A power n, B power n is a DCFL that belongs here. WW power R is a CFL that belongs here. Machines, if you see, DPDA here, NPDA here. This is the clear classification of these languages. Every DCFL is CFL, but every CFL need not be DCFL. There are some languages belongs to this region. There are some languages belongs to this region which are not accepted by this machine. So there are some languages accepted by this machine, not accepted by this. There are some languages belongs to this region, but they will not fall under. That's why in this classification is not there in regularity. We don't find this in regular. In regular everything is same, but here because of different expressive power, the language classification also done. There are some languages, so whenever we are detecting context free languages, you should know what is deterministic context free, what is normal CFL. So if I speak about this one, WW power R, WW power R is CFL, but not. This is the way of detection of CFLs and DCFLs differently. This is a CFL, but not a DCFL. It is not a deterministic context free. So this is about the way of classification of languages, CFLs classification, identification of how DCFLs and CFLs are differentiated based on their expressive power of the automata. So this is a easy one. Still, if anybody having any confusion here, you can ask me. You try to construct by your own. Still, if you have doubt in today's session, you can ask me in next session. Right. So with this, we can stop for the construction of PDAs. Based on this knowledge, we can directly move to CFL detection, detecting whether the language is accepted by PDA or not accepted by PDA. Right. Let me give one language here. So all this is about PDA possible or not, push down automata possible or not. Push down automata possible, we can say CFL, push down automata not possible, non-CFL. So there are two languages here. Let me speak about these languages. So these are the two languages, very important languages, many times asked in previous papers as well. Now the question is, which of this language are both of these accepted by PDA or not? So the language, see this one, we can construct these two same, these two same. So we can make a logic, yes, we can push into the stack whenever is so to identify whether it is CFL or not, context free language or not, PDA logic possible or not. Now the question is how to check which is CFL, which is not a CFL. Today our topic is a construction of CFLs. Identify logic, whether it may be a non-deterministic logic or not an issue. Even if non-deterministic logic also exists, fine for us. So any logic possible or not. See here for L1 we can make a logic easily. So for L1 is 2 A's, assume 3 B's, 3 C's, 2 D's. So A's and D's are equal, B's and C's are equal. We can clearly make a logic. A's push into the stack, B's also push into the stack. The logic is very clear here. Till this part everything you push into the stack. First A is pushed into the stack, B is pushed into the stack. After that, C's and B should be same, no? So 1C, 1B pop, 1C, 1B pop, 1C, 1B pop. Then 1D, 1A pop, then 1D, 1A pop. The logic clearly works. Whatever the framework structure of PDA is there, for that this logic clearly suits. So if I make that logic, if I construct, the automata can be a DPDA or NPDA, you can construct. Then PDA clearly possible, so this comes under CFL, context free language. This is the way we can detect which is CFL, which is not a CFL. So in order to tell whether a given language is context free language or not, what you need to do is, our previous 3 classes, whatever we studied, its knowledge we have to use. So whether that logic is possible or not. To construct PDA, what is the PDA? PDA is nothing but logic. That's all. The logic you show by transition diagram or transition notation, whatever it may be. So that logic is called as a PDA. So that common logic, whatever is there to accept these strings with our available framework, that is finite automata plus stack, can we construct the logic or not? Clearly for the first one, logic is there, PDA possible. Can we construct a similar logic for the second one? The second one is number of A's and C's are equal, number of B's and D's are equal. So if 2 A's, 3 B's, A's and C's are equal. So 2 A's, 3 D's. So we need to make a comparison here. We need to make a comparison between A's and C's. A's and C's. So for that, A is pushed into the stack. There are only 2. Okay. A is pushed into the stack. Then B's. B's also we need to push into the stack because there is no comparison between A's and B's. Whenever we have a comparison, then only for that symbol we have to perform pop. A is pushed into the stack, B is pushed into the stack. Then C encounters. There is a comparison between A and C. Then 1C, 1A pop. 1C, 1A pop. This we have to do actually. But is it possible with the stack? What is stack nature? Last in, first out. Can you pop out any symbol from the bottom? No. So this is clearly violation of our framework. So whatever the comparison exists here, this will not suit for our framework. What is our framework here? Finite automata having one stack. So this language will not suit for our framework. That is not suit for push down automata. Framework is nothing but push down automata. So clearly we can say this is not accepted by PDA. We cannot construct any PDA for this. These two looks almost same, but there is a lot of difference in this. Lot of difference. So for this language, not possible. For this language, possible. That's why we can say this is a non-CFL. Logic not possible to construct PDA. So for this we can make a logic. This is the logic for this. There is a logic, but for this logic not exist. So whenever you want to identify a given language is context free language or not, the only thing is PDA. That's why we practice PDA that much. So PDA possible or not, the logic of the PDA possible or not. If the logic of the PDA possible, conclude as CFL. Logic not exist, not CFL, not a context free. In the context free also differentiation, whether it is just a CFL and DCFL, CFL but not DCFL. Whenever you look about any language, these 4 things, whether it is context free or not, whether it is non-CFL, whether it is a CFL, non-CFL, CFL but not DCFL, CFL and DCFL. So all these 4 things you have to get in mind. So that is what we need to practice. So now, so these two asked 2 or 3 times in GATE paper. These two are very, very important languages. So you just observe this, try by your own once again. Once again. So the way of detection of which is CFL, which is not a CFL is in this way. Let us go for one more. Logic. Now onwards, whenever I am detecting any language, I am simply making based on a logic possible for that language or not. That is what my intention. No confusions here. So this is completely based on the knowledge of pushdown automata. If anybody don't have a pushdown automata knowledge, just go through the previous lectures, watch PDA properly, recordings available, then you can solve the CFLs. So if you want to solve the questions of context-free language, pushdown automata knowledge is must. Right. Let us see some more questions here. Let us try to take some selected questions. Come to the first one. So I think in the last session, I told you this one. A power n, B power n, C power n greater than or equal to 1. What about this? Is it a context-free language or not context-free? Can we construct any logic? So whenever you say CFL, whenever you want to verify anything is CFL or not, whether a logic is there or not there, we need to find. What is the comparison here? Number of A's and number of B's are equal. Number of B's and number of C's are equal. A should be equal with B's, B should be equal with C's. So can we make any common logic to accept this? With one stack it is not possible, because see, we push A's into the stack. Then for 1B 1A pop, for 1B 1A pop, this is okay. A's and B's equality we'll check. What about number of C's? C should be compared with B's. C should be compared with B's. For that, B should present in the stack. But where B is present in the stack? If you push B's into the stack, this comparison will not be maintained. That's why this comparison as well as this comparison, if you want to maintain at a time, this framework of our pushdown automata, only one stack will not be suitable. So we cannot make a logic for this. With one stack it is not possible. That's why two things clearly we need to identify. To accept a language by PDA or to construct a logic, the thing is, it should, that language structure should suitable to our PDA structure. Where it fails, more than one stack requires, then it fails. Stack property, last in first order not there, then also fails. So you have to observe these two things clearly. So here more than one stack is required. So this is clearly a non-CFL. Non-CFL. Right. So now let us solve one more question. Look at the first one. We will take some selected questions. If you want, you can solve by your own. What about the first one here? It looks like the previous one, A power n, B power n, C power n. Looks like the previous one, but here n value is n value is greater than or equal to 1, but here n value is at most 10. So it is a finite language. Finite language. So we made a classification on finite languages. Let us try to see. Finite languages are there here. Every finite is regular. Every regular is CFL. This is the clear relation between these three. If a language is finite, it should be regular. If it is regular, it should be CFL. This is the relation between these three. That's why once you need to identify whether it is finite or not. Once it is finite, regular, CFL. So the classification we can give for this type of languages, it is finite. So regular. Every regular should be CFL. So CFL. So this language, even though it seems to be having multiple comparison, A power n, B power n, B power n, C power n. Even though having this many multiple comparisons, not a problem. This is clearly a context-free language because it is already regular. If it is regular, should be CFL. That is. Let us come to the third one. What about third one? A power n, B power m, C power n, so n greater than m. So many comparisons are there. But look at the language. N comma m values at most 1000. So language becomes what? Even after having these many comparisons, we don't worry about that. First we'll check on finiteness. If it is finite, this is clearly a finite language. Then it is regular. If it is regular, then it is CFL. So you need not to worry about finite languages. Finite languages are similar as our regular languages. What we studied in regular language, same concept for finite languages. Finite should be regular, regular should be CFL. This is the way we'll check for finite. There is no confusion, no difficulty in finite languages. Whenever a language is infinite, then we have to solve them clearly. Right. Let us see some of these languages. Let us take selective language on this. This is not a by, this is a such that. Whenever infinite, all these are infinite languages. Whenever infinite language exists, we need to check for the comparison. If one comparison exists, if that language structure suits for our PDA framework. So can we make this language like this? In the place of n, 2m plus 1, b power m. the language is becoming this way. Here every A is 2m plus 1 times more than B's. Comparison exists, but PDA having a stack, so it can handle one comparison. That is also suitable for our framework. If having one comparison, and we can make a logic with our PDA framework, so one comparison is okay. This is clearly a CFL. But what about regularity on this? Whenever you check regularity, comparison exists, so it is, but not regular. But not regular. Now come to the 9th one. Let me jump directly to the 9th one. Oh, instead of 9th one, it is 10th one is better. 9th one is okay. So a power n, b power m, n equal to m square. A power n, b power m, m equal to n square. So if I replace this, in the place of n, if you take m square, the language looks like this. In the place of m, if you replace m square, b power m. Okay. Now seems to be having one comparison. But see, here we have a finite automata. Whenever you are generating string from the symbol, common difference. The finite automata major problem is, if we have a common difference, then only we can maintain that in states. Whenever we have like this, the states concept is not suitable. So even the one comparison, so that's why I am saying just comparison is not enough. Having one comparison, so it should suitable for our framework. Whatever the PDF framework is there, finite automata plus stack. Here stack and everything is okay. It fails for the finite automata framework itself. That's why this is clearly a non-CFL. A non-CFL. So many questions of this type we found in GATE papers, in previous papers. If you see previous papers, there are so many questions of this type. So just remembering something is not sufficient here. To detect CFLs, you should have a clear understanding knowledge about finite automata. You should have a clear understanding of pushdown automata, deterministic, non-deterministic, overall knowledge. Based on this, the language questions we can solve. So language question solving is just not simply solving by just looking at. Right. Let us come to the 10th one. A power n factorial, b power n factorial. It seems to be having one comparison only. There is only one comparison. What is there? Even though having one comparison, the factorials, whenever you generate a strings from the factorial on this, no common difference. Common difference not, so it will not suitable for our finite automata framework itself. So this is also clearly non-CFL. Non-CFL. Like this. So just to check for a given language is context free or not. Pushdown automata logic, can we make it or not? How many comparisons exist in that? Whether one stack required or more than one stack required, or whether it is suitable for finite automata structure or not, whether it is a finite language or infinite language. So overall, based on this whole knowledge, by keeping all these things in mind, we can say a given language is a context free language or not a context free language. Like this, we have so many things here. We can check. There are so many things. some of these are CFLs, some of these are non-CFLs. So you can take these examples, try by your own, which is a CFL here, which is not a CFL. Any doubt in this, if you are facing any difficulty anywhere, so you can ask me. This is, you can take this as a homework also. Identify based on our previous knowledge, which of this is CFL, which of this is not a CFL. So these type of questions generally will get in gate papers. Still anybody having any doubts in this? So you can easily, we can try. If you are not getting, ask me in the next class. So this is about CFL detection. We identified what type of language comes under CFL, what is not a CFL. So with this, we can close this today's session. We'll continue from tomorrow. Tomorrow onwards, we'll start with a new concept of theory of computation, some other concept. If you have any doubts on context-free languages, you can ask me in tomorrow live session. I can clarify your doubt. Okay. Okay, students. Thank you. See you in the next session. Bye bye.